So today we're going to be working on power series again, but this is going to be the second part. This is going to be like the more advanced applicational part. So if you remember, right, the sum from n equals 0 or any number to infinity of a number r raised to the nth power with something out front equals 1 over 1 minus r, right? Because this would be a simple geometric series, and then that's the sum of that series, right? So relating this back to what we know, that means that you can write f of x equals 1 over 1 minus x. This is the same thing as the sum from n equals 0 to infinity of x to the nth power times an a value up top, which is actually equal to 1. So times 1, right? And this is very important because this proves that that over there is equal to this. But we know that this value would converge only if the absolute value of x is less than 1, because that's the requirements for this to equal this, if you remember from simple geometric series. So that means that we can rewrite different functions which are in the form of a over 1 minus x, this x value can be anything, is equal to the sum from n equals 0 to infinity of ax to the nth. And that would help us because then we know like the radius of convergence for this and what the value is and all of that. So let's start off with an easy problem. Here I'm going to rewrite that up top. Here I'm going to just write that over here. So here, let's work with the simple problem of transforming one of these into this. So let's go 1 over 1 plus x cubed. So f of x equals 1 over 1 plus x cubed. Now, as soon as you see this, you can see that the a value is actually equal to 1. So let's write that down, a equals 1. And now you need to be able to manipulate this into the form where it's 1 minus something, right? So we can rewrite this as cubed, right? So now you're left with So now this value right here is the x right there, right? So now you can rewrite this as the sum from n equals 0 to infinity with the a value. And we can do x equals negative x cubed. And now the a value is equal to 1 times the x value here is equal to negative x cubed to the n. And we know that negative x cubed, the absolute value, has to be less than 1, so then the r value equals 1. I don't think that we need to go over that much because this is pretty simple, right? You just take the cube root, and since there's an absolute value, this turns positive. Okay. And the interval is from negative 1 is less than x is less than 1. And you could check to see if that converges or diverges. Yeah, that's irrelevant. And now we're going to be left with neither one of those converge because -1, if you plug it in here, be 0. Moving on, let's go on to the next problem. That one was kind of simple if you followed along. And the next problem is going to be f of x equals 2x squared over 1 plus x cubed. Now this might look confusing because you have an x on top and the same thing on the bottom, right? But if you remember, you can have any a value on top. It could include an x if you want, it could include anything, right? So this value right here, this 2x cubed is just your a, right? So let's write that down. A equals 2x squared, right? And now you're left with a over 1 plus x cubed. We just solved that, right? So it was a over 1 minus negative x cubed. So now your power series is going to be the sum from n equals 0 to infinity of your a value, and then it's the same thing, right? So absolute value of negative x cubed is less than 1, and then x equals 1, so -1 is less than x, which is less than 1. And then you can look at this, you can see that your x value is here and your a value is here, right? So now you get 2x squared times negative x cubed to the n, right? So this is the same as this is -1 to the n times 2 times x squared times x to the 3n, which is x to the 3n plus 2. And then that's what your value is, right? And now let's go on to our final problem before we learn something new. So now f of x equals x over 5 minus x. So there's still an x in your numerator, but now this value does not equal 1, right? So we've got to be able to change that. So first let's find out our a value. A equals x, because that's all it is. So now you have f of x equals a over 5 minus x, right, as seen here. And you can just plug in a if you want, it doesn't make a difference. But now we've got to change this to a 1, so we can just factor out a 1 over 5 from this entire thing, right? So now you would get f of x equals 1 over 5, because you're pulling out a 1 over 5, times a over 1 minus, and then you've got to divide this x by 5 as well, right? X over 5. So now you see that you're in this form right here. So you can write this into a power series, right? So first you need to find your interval of convergence. So absolute value of x over 5 is less than 1, x is less than 5. So your r value is equal to 5, so -5 is less than x, which is less than 5. And now moving on, you can write down your actual power series, which is equal to, remember there's a 1 over 5 here, so that's very useful, that's needed. This 1 over 5 doesn't just disappear, so it'd be from n equals 0 to infinity of your a value, x, times this 1 over 5, times what is your x value? x over 5 to the n. So now you can rewrite this as 0 to infinity of, since there's a 1 over 5 and an x, this is equal to x over 5 to the n plus 1. See, that wasn't too hard. Now we're going to be going on to the harder part of this. And that is taking the derivative and the integral of power series. Which isn't really that hard, but, you know, it can be. So the main thing that we've got to remember is when you take the integral and the derivative of a power series, your r value remains the same. So given that f of x equals the sum from n equals 0 to infinity of a times x to the n, right? F prime of x equals the sum from n equals 0 to infinity of, this is just a simple power rule, right? Because the only variable that you're taking the derivative for is x. And x is raised to a power, right? So then it'd be a times n times x to the n minus 1, right? So that's the derivative. And now taking the integral. So given that small f of x equals n equals 0 to infinity of a times x to the n, then the integral of f of x equals the integral of right? And then this is the same as big f of x equals so there's actually a rule which states that the integral of a sum is the same as the sum of the integral. So you can rewrite it like this, and then n equals 0 to infinity a times x to the n plus 1 n plus 1 plus c, right? And then those are two very important rules. Right, and then this doesn't always have to be just x, it can be x minus a, it could be whatever. Right, because it doesn't always have to be centered at 0. So now let's move on to a problem where we can apply this. So given that g of x equals 1 over 1 minus x whole squared, let's find the power series of this. So right off the bat, we can tell that g of x equals the derivative f prime of x if that equals, wait here, this is a bit confusing if you listen to this without volume. So let's say f of x equals 1 over 1 minus x, right? Then we know g of x equals f prime of x, right? So this is a very simple power series, right? So f of x equals the sum from n equals 0 to infinity of x to the nth, right? So now you can find f prime of x, right? Using this right here. So then f prime of x equals the sum from n equals 0 to infinity times a is equal to 1 times n times x to the n minus 1. And since it's the derivative, the radius and the intervals will remain the same. So the r value equals 1 because this is the most basic one. And the interval is -1 is less than x, which is less than 1. So this problem was fairly simple. So we can move on to what might be a bit more complicated problem, but there's only one way to know. That's if you do the problem. So let's go with what do we notice here? This function right here is the integral of the opposite of the integral of 1 over 5 minus x, right? So we can rewrite this as h of x equals the negative integral of 1 over 5 minus x. So then h of x equals the negative value of the sum from n equals 0 to infinity of, we had actually figured this out a bit ago. I think that the value was x to the n plus 1 over 5 to the n plus 1, right? No, it was not, because that was x over. So it was just x to the n over 5 to the n plus 1, right? And now we can see that we've got to take the integral of this, right? Dx, which equals the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1 times 5 to the n plus 1. As you can see, I just used this right here, and I just applied it as the a value is 1 over 5. There's an n plus 1, and then the n plus 1, and then I forgot the plus c. This is all times -1, right? So negative c is the same thing as positive c, so you can rewrite this as c minus the sum from x So we aren't actually done, because you have this c value here, and you can solve for it, right? If you plug in a value for x, then you could isolate c. So the easiest value in this case is 0, because then this entire number here will become 0, right? So here, let's do that. Let's plug in 0 for x. So now you get c minus the sum from n equals 0 to infinity, 0 to the n plus 1 over 1 times 5 to the n plus 1 equals ln of 5 minus 0, right? So this value equals 0, this value equals ln of 5, and now you get c minus 0 equals ln of 5. So now you get c equals ln 5. So now your final answer here is that the power series representation, so ln of 5 minus x equals ln 5 minus the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1 times 5 to the n plus 1. So basically, as you can see, right, if you have a function like this that isn't easy to write as a power series, right? Like, how are we supposed to be figuring this out from this? You can relate it to a different function that's either its derivative, that this is either that function's derivative, or this is either that function's integral. And then using that, we can relate it back to this rule right here, one of these two, which are actually very easy to derive on your own because of the fact that this is a constant, and then this value right here is just an application of the power rule. So you just bring the n down, or it could be like n minus 1. You can take like second derivatives, right? Like in this case, f prime of x equals a times n. That's still a constant. Wait, I forgot my summation sign. The sum from n equals 0 to infinity of a times n minus 1, because you just bring it down, times x to the n minus 2, and then like so on. And then the integral is also easy because it's literally the same thing. It's just an application of like the reverse power rule, as it's called. But then you would need like cx, and that's a bit more complicated. But it's like still a fairly simple thing for you to be able to derive on your own. But when given functions, you should be able to apply these and get to your power series version of them. Because when you're given the power series, like in this case, we know that the radius of conversion, for this function right here is equal to 5. And that's the same as the radius for this function, right? So the radius and the intervals will always be the same, as well as the center, as the center does not change either. So here, let me write that down right here. The radius and interval will be the same for the derivative original and integral. Okay, well, that's about all. Hopefully this helps somebody. I feel like this is going to be some of the more hardened material. It's definitely going to be getting harder with like polar coordinates and stuff. But hopefully this made this section a bit easier for y'all.